Artificial intelligence has become one of the fastest emerging technologies in the past years, and especially machine learning uses the possibilities of big data to optimize processes, find new solutions, and sometimes also give new insights. So the aim of my talk is to give an overview of machine learning tasks for creating music notation. These are topics we at Capella Software are working on to improve our software. And in the next talk, Mike's talk will show you more application in music notation. So here's the agenda. After a short introduction to machine learning, I will basically present 3 tasks that apply machine learning to music. Better like this? Okay. Machine learning to music, which are optical music recognition, music transcription from audio, and algorithmic composition. So many years ago, I was working in a research project entitled Information Structures in Music. The goal of this project was to model musical structures with methods used in computer science. And from the results of this work, there came out the software Tonica Fugata, which I will show you later. After some years I was working in Munich as a software engineer. I also helped out to build an online music editor, Scorio. Scorio enables users to write music directly in the browser. So they can go to the website, write music in the browser, and Scorio uses the Lilliput engine as a backend. Since 2016, I'm employed in Capella Software, and what we do is that we create easy-to-use and intuitive music software at moderate prices, and which are aimed at individuals, music groups, and associations in the amateur and professional area. Sometimes asks why Capella spells with 1 P in contrast to a cappella music, which writes with 2 P. So the explanation is quite simple. Capella does not stand for the term as in cappella music, but it comes from capella, which is a brightly shining star, more exactly the star system in the sky in this constellation, Auriga. So that's where the name was originally derived from. Well, in this sense, these are our Capella stars. So the software which is distributed by Capella Software. Our main program is the music notation program, Capella. Its current version 8 comes with a completely redesigned user interface, optimized for usability, and is available both for Windows and Mac. And I invite you, after the talk, when you have time, to visit our booth outside to get to know more about our software. However, in this talk, the focus won't be on Capella, but on 3 other programs, which are Capella Skin, Capella WaveKit, and Tonica. So after this short introduction, let us dive into machine learning. And well, there have been many prominent achievements recently in machine learning, and I just want to mention a few to give you an idea what different areas of machine learning have been there, and then switch over to the music notation part. So in 2015, the software AlphaGo was presented, which was able to beat the best human Go player, which before was unthinkable. I say 10 years before, there were many claims that it would never be possible to play a human Go player because the complexity of the game Go was too high. In 2015 it happened. 2 years later, Google presented AlphaZero, which was able to be the best engine, the best chess engine, which is actually better than our current world chess master Magnus Carlsen. And what is really astonishing in this achievement is that it uses almost no prior knowledge. It just uses the chess rules, nothing else, and from this knowledge, just by playing against itself, it learned to, it reached this high level of chess play. And this just after playing 24 hours against itself. And that's really astonishing. Well, this is one of the, say, highlights, but what is a more common application, or currently very common application to machine learning, is image recognition. In this case, we have here images of flowers, may have different size, and the task of the program is to classify them. So we have daisies, sunflowers, roses, tulips, and the software is presented with different images of these flowers, and afterwards it has to, for new images, it has to say what kind of image has been presented. Another application which is currently discussed a lot is autonomous driving. In autonomous driving, real-world objects like cars, buses, persons, and so on, in a video stream are found and classified in real time. And the final example for machine learning is in March 2019, Google prominently presented an application on the start page, which harmonizes melodies in the Bach style, and it uses a neural network which was trained with 306 Bach chorale harmonizations. So after these introducing examples, what is behind all these applications? When we are talking about neural networks, or more precisely artificial neural networks, we mean that computing systems which are inspired by the brain functionality. They are typically suitable for tasks that are better solved by intuition than by rotes. This might be unlike many aspects in music notation, because in music notation we know that many aspects can be widely described by rotes, as we know from Elaine's book, Behind Bars. So that's not the kind of task which is appropriate for neural networks, but it's more when you look at an object and you immediately know what it is without exactly describing it with certain rules. So that's kind of intuitive behavior can be very well simulated by neural networks. When we talk about deep learning, which also arises in this context very often, we mean large neural networks with many hidden layers of neurons. And one special instance of deep learning is so-called convolutional neural networks. Convolutional neural networks are deep networks using so-called pooling networks for information compression. I'm not going to detail what this exactly means, but you can admit that kind of abstraction is reached by doing this kind of information compression. And, well, we have to say artificial neural networks are not new. They exist since almost 50 years now. So the first idea, the perceptron, is 50 years old now. But it has improved a lot in recent years. And that is basically thanks to the increased computational power, which now allows to deal with large networks which at my time at university in 2000 were unable to deal with. So here's an example of a convolutional neural network model for vehicle classification. Basically, if you look at the image, we have on the left side the input, which is a vehicle image, in this case a car. We have the output, which is a list of vehicle classes like car, truck, van, bicycle. And in between we have a twofold network structure. There is the feature learning part and the classification part. The feature learning part does kind of automatic extraction of features. So it captures spatial and sometimes also temporal dependencies in an image through the application of these so-called filters. Whereas the classification, the latter part of the network, then assigns the image to a class based on the learning features which have been determined before. So now, we have not talked about music until now, so we will dive a little first the first task, which is about optical music recognition, and which is, I think, the most prominent application we have currently have in music, in the application of music, machine learning to music. So our software, Capella scans music from paper or from PDF. And as you can see, the recognized symbols, text have green color. So as you see in this image, usually the recognition is very good if the quality of the print quality is very high. So typically we have a recognition rate of more than 95%. However, it decreases with a lower print quality, or if you're dealing with, in this case, with handwritten music. So our motivation is to improve the recognition of sheet music with lower print quality as well. If we look at the optical music recognition process in general, there are two steps of interest involved here. I don't go into details of the whole image, but concentrate on the writer part, which is the one step is music symbol segmentation. The second one is music symbol classification. And all these steps together are also called music object detection. So what does it mean? I just give a very small example. Here's a score excerpt as an example. And after segmentation, we get possible objects that are localized but not yet recognized. So we know where they are, but we don't know how they're called. And after classification, the segmented objects are recognized with a certain probability. For example, we have the note head. Here's a full note head, which is recognized with a percentage of 99%. So the network is pretty sure that it will be a full note head. So the application of this CNN, or convolutional neural network model, to music symbol classification is quite straightforward. What we do is that we extract the music symbols from a sheet, from a music sheet, in this case a clef, and the output is just the symbol class, in this case multi-clef. So we made some experiments with music object classification and detection, and we got very smooth learning curves. So the accuracy on a test set, which is shown here in the blue color, is not used during the training process, rises together with the training set, which is shown in red color. And what we can see that almost no overfitting takes place. It means that the network really has understood the data and it just learned it by heart. So summarizing our results, I won't go too much into the details. That we got very impressive classification rates, that we had a relatively short training duration. If you use the graphic processing unit on a CPU, it was too slow. And it works well for simple models also. There are different instances of CNN models, and with simpler models we got very good results as well. And the classification performance was also quite okay. So it took about 1 minute per page to classify all objects on this page. So this is the classification part. This separation I've shown before between segmentation and classification has a significant drawback. if the segmentation is incorrect, the classification will not deliver sensible results, and therefore what object detection models, is now the second part of my concerning music object detection, identifies and classifies image and objects in one step. You can imagine that this learning task is much harder than a pure classification, because you have to learn additionally object position and must be learned at the same time as the classification. This is active, current research active, and I would like to mention Alexander Pacher from Vienna Orchestra, which is dealing with this topic and is doing great research here. So, we did our own experiments with these models, and our first results were quite poor. So, as you can see here, some objects were detected, but not very many if you fit in a whole page. So, there were simply too many objects per page. And if you think back to the autonomous driving example, where we classified cars and so on, so we typically had up to 10 and 20 objects per image. But here we sometimes have to deal with 1,000 and more music symbols per page. So our next attempt was to concentrate the definition at the music system level. And you can see here, now the classification, the result of the detection is much better than before. So there's still some objects which are not recognized, but many objects are recognized, and some also with very high probability. And what is another good news is that we also got good results on handwritten music. So if you fed in data from the so-called Muskema dataset, which is a dataset with handwritten music, as you can see here, this has been done on a system level, and I have now put them together in one image. There's a very high recognition rate on this image as well. So I think, to conclude this part about optical music recognition, that this is a really promising way for improved optical music recognition in the future. I come back to the task, and now we go from sheet music to audio. Our software Capella WaveKit recognizes notes from an audio recording. It creates a so-called sound tissue, a German Tonteppich, from the sound data, which is then used to detect individual notes. So, as you can imagine, this is even a more challenging task. If you think to yourself, if you listen to symphony, you will be able to recognize harmonies or individual voices, but typically you won't be able to reconstruct the entire score. So it's even harder for a system to do it. So this is active research in progress, and I just want to present some ideas that might lead into the direction where we could proceed. So the main question which has to be answered when addressing this topic is that currently the CNN architectures are very highly optimized for image processing. And the question we have to answer is how to use them for audio processing as well. Well, if we want to find an analogy between image and audio, we can look at the spectrogram, the Fourier transform of the audio source, and see it as an image. This seems to be quite reasonable. However, if you look a bit closer, the analogy is not perfect. Well, mainly the note that sound at different frequencies. So, in contrast to what we have seen with the images, we cannot easily localize a note, but we have to look at the harmonics as well to get to find the real note which is sounding together with the overtones. That makes it harder to detect. And another point I feel, given an optical analogy, is that the notes sounds simultaneously, so we have a lot of interference between them. As you look at this image of zebras which are overlapping, you can imagine it's much harder to detect them as if they would be separated in the image. So, the main precondition for learning is the identification of places where notes are starting. And we did some initial experiments where we generated audio data, and after training, the note onsets were correctly identified in real recordings. So this worked quite well, but it's, as you can imagine, just an initial step for dealing with the complex task of audio recognition. So what are the learning tasks which might be improved with neural networks? These are the detection of note onset, beat and measure, the estimation of pitch and key, and finally the recognition of instrument and voices, which result in a complete music notation. So here's a hypothetical model for note identification. The note onset regions might look like this. We have an input which is a note onset region, and the output then is just a set of multiple classes that mean notes sounding at the same time. But as I said before, it's just a starting point, and there's a lot of effort which has to be invested here. So my final task will be about rhythmic composition, and I will close with this one. Our software tonica, which I mentioned before, composes and analyzes scores, variations, accompanying patterns, canons, and fugues, and solves practical musical tasks like melody harmonization and figured bass realization. And it already uses neural network technology to accomplish these tasks. A possible CNN model for melody harmonization might look like this. So the input is the melody and the output is the harmonization. However, tonica only implements the classification part, the latter part of the CNN. It means that the first part of the network is omitted, and instead, in contrast to the CNN model, tonica uses features that have been determined experimentally. So we used prior knowledge, musical knowledge about harmonies and note relationships to determine these features, which are then fed into the network, into the classification part of the network. Now it's your turn. I have two chorales here for the same choral melody. Please listen to them and afterwards tell me. One is from Bach and one is from tonica. That the first one is a Bach chorale? Okay. Who believes that the second one is a Bach chorale? Okay, great. Successful. Great. Indeed, the first one is a Bach, and we'll have found the passages where it really sounds a bit like Bach, but it's not really Bach. And we made a similar experiment with our customers. So we made a kind of Moodle online quiz where we presented them with 10 chorale pairs, and we had more than 800 participants, which were Capella users. And here's the result. So as in your case, the most of the participants correctly identified them, so 62% classified them correctly, but at least 38% did not classify them correctly. So there's still, as you can see on here, you heard, there's still room for improvement. But if you want, you can try the test on the website. If you look at the URL below, you can make the test yourself and see whether you will be fooled or not. Okay, to conclude, the challenges that are related with this kind of topic are very general. So in this case, we really can't talk about big data. We have 350 Bach chorales, but unfortunately we can't ask Bach to compose us more chorales. And also the Bach chorales have homogeneous structure and style compared to other composers. So we have to say that the learning success is certainly restricted by the available amount of data we have. And another thing that would be interesting is to see whether a CNN would be able to find the features we currently determine manually, also find it automatically. Well, this is would be interesting because maybe it finds totally different features from what we think are relevant. Thank you. That's just to summarize my talk. I think that artificial intelligence reports will grow in the next decades and it will change our lives, definitely. And although machine learning will not revolutionize music notation, I think that there are specialized tasks around music notation that may be improved using machine learning. Yeah, that concludes my talk. Thank you for attention.
Thank you very much. A few questions?
Yes. So if I participate in a lottery which has a 95% chance of winning, then I will take that. But if you say, oh, it's great, it has a 99% confidence in recognizing a symbol on the page, how useful is that? Because on a page with 1,000 symbols, that's like 50 errors or and quite a lot of errors.
Yes.
So for actual real use, how good is it?
Yeah, I mean, if typically you omit the recognition of symbols which have classification less than 50%. You usually omit them because it's not you're not sure about the results. But if they have more than 50%, you can take them into consideration. And what you can also do that you might use several models in parallel and make them predictions together, and then put them together in kind of team of experts, and then see that if there are or some of these experts agree that this might be a possible relatively high probability reasonable classification, then you decide to take it. Otherwise, you leave it. That might be a possible strategy to deal with these uncertainties.
But have you tested like these kind of systems? Have do real users use them, and at what point do they say, okay, this is too good?
Yeah, this is still research in progress we are doing here. So we have not yet experimented with users, and so that will be now the next step will now be to find an implementation. Also, maybe combine these achievements we have here with our current object music detection, which is not neuronal, and then to see whether we together might improve the overall result.
You described it as stripping out the staff lines so you can segment the data, so you can detect this alto clef. And then you're talking about the difficulty of retaining the positional data with relation to that. So can you talk a little bit more about that?
Well, these object detection models, the application to music is not, normally they're used for in settings where we have, as I said before, we have only few objects in a image. So they usually are very less performant than the classification. So they take a lot of time to identify the regions where objects are placed and also to classify them afterwards. And typically they are usually at the moment the objects are not appropriate to deal with too many objects per page. It's just a restriction which is currently existing. It might fall in the future, but at the moment they are not appropriate to detect objects in an entire page. And therefore we simplify the task by telling them, okay, we use a smaller part of the page and restrict it to maybe a maximum of 100 objects per page, which simplify the tasks.
The registration aspect of it, between the staff lines and the object, is crucial to the performance.
Yes, it is. Yeah, it is.
And how do you solve that problem?
Well, I don't know, I'm not sure whether I got the point exactly.
Like the difference between an alto clef and a tenor clef.
Okay.
How would you distinguish that?
Okay. The training data will be labeled. So if we have an object, we tell them before that this is an alto clef, this is a tenor, a treble clef, this is a note head, and so on. And this data will then be used during to train the networks, and afterwards they try to find objects which are similar to the ones learned.
But because the alto and the tenor clef are identical, how would it tell the difference?
Okay, I understand. Okay. Yeah, in this case, it will probably it will set them in the relation to the lines, because they get into this additional information which they extract from the sheet. Yeah.
I don't have so much a question, but a couple of observations. We've been using optical music recognition for 20 years successfully, and so in my opinion, what matters isn't getting 100% recognition. It's that the process of recognizing the music, using the software, and then making the requisite corrections by a human, and you add all of that time together. If that's faster than entering the whole thing by hand, then it's worth doing. And we save an immense amount of time doing things that way. But you have to just lower your expectations a little bit. And the second thing is, if you filter out, don't even try to recognize a certain class of objects, the recognition rate gets much higher. So in other words, it's another case of lowering your expectations. So if you're using it simply to capture the notes and rhythms and nothing else, it's a pretty efficient way of doing things. And of course, with time, I expect your software and others will become much better at recognizing all of the additional harder to recognize stuff. For the moment, it's perfectly possible to use as long as you lower your expectations a bit and try and do it as efficiently as possible.
Yeah. I think that both things you mentioned matter. It matters that we get not 100%, as you say, but a very high classification rate. At the same time, we need to efficiently also correct recognize which have not been.
And one more observation is if there's if the editing engine for making the human corrections is a good one.
Yes, that's important.
That makes a huge difference.
Definitely, yeah. But one aspect that I mentioned also in my talk is that we specifically try to address scores with a lower print quality. And in this case, I don't know what your software does, but if the print quality decreases, usually also the recognition rate will decrease. And therefore, this is an aspect where we can go forward if we get better basic recognition.
What we do is, if we receive a photocopy, what we will quite frequently do is we will go to the local music library and borrow the original book for instance, and
Yeah.
scan that.
Yeah.
Because
Yeah.
scanning from a printed book
Yeah.
it works much better than from a photograph.
That's good.
Last question, please.
Mhm.
So how much of your time or resources is devoted to ethics related to machine learning?
Well, these are initial experiments we have now done. Until now, our software, with the exception of Tonica, does not use this kind of technology. But these are ideas we are going to invest now in this direction and to see whether we can significantly improve. I don't tell that it will be successful, but I think it leads in a good direction, and we will try to invest some time to see how we can effectively improve our existing recognition algorithms. And it depends. If we see that there's a lot of gain we can get from it, we will probably invest more time in it, but I can't tell you at the moment.
Thank you very much.
Okay.
He is a very